Alright, welcome to Nicolay College. My name is Warren Krause. I'm going to go through gas metal arc welding. We're going to start on chapter 10. Before we actually dive into a lot of the content, I want to explain to you what gas metal arc welding actually is. Basically, it's GMAW is how it's represented. G actually stands for gas. Now, typically you say gas, that means a shielding gas. Depending on what process that we're going to be using, if it's short arc, if it's spray, pulse spray, whatever process we're going to be using for GMAW, that means we're going to be using a shielding gas. Metal, that actually tells me there's going to be two types of metals that we can actually weld with this process. Typically, we're going to be using what they call ferrous metals, which is your carbon metals, your steel, things like that, cast iron. We're also going to be using non-ferrous metals. Non-ferrous metals are like your aluminum, copper, things like that, things that do not contain carbon. Next, we're using with the word arc. Arc actually stands for, you're going to be using electricity. So you need a power supply. You need the current to be traveling through this process. And welding. Keep welding simple. Basically welding, you're just joining two pieces of metal together. Joining metals. So, GMAW, gas metal arc welding. We're going to be using a shielding gas. We're going to be welding metal. It could be ferrous or non-ferrous, like I said, aluminum, carbon. We need an electricity supply. That's how we actually melt and fuse our metals together. And welding. So, this is also called what they call MIG welding. MIG welding is kind of like a shop lingo term. So MIG is what they call metal, inert, gas welding. So metal, inert, gas welding, like I said, these are, it's also called, it could be used MIG, metal active gas. And then we'll go through what inert gases and reactive gases are when we get into our shielding gas section of the chapter 10. So yeah, MIG, GMAW, they're all basically the same. Now, GMAW, this can be what they call a semi-automatic welding process. Semi-automatic welding processes means that it's semi-automatic. So that means you actually have to hit the trigger. The wire is being fed automatically for you, but then you actually have to control your arc length, angle, your travel speed, and whatever other variables that you're going to be using for it. It's also fully automatic. What does that mean? That means you program a robot to do this. The robot is doing everything for you. Typically, in our industry, the semi-automatic is probably the most common. That's where you actually grab your wire feeder, you feed it, the machine is feeding the wire for you automatically, and you control all the variables of the welding process. So lots of difference between semi-automatic and fully automatic. Now, one main reason in industry why we use GMAW is because it has high deposition rates. What is your deposition rate? This is how much metal you're actually putting down. It's a very high efficient. It goes anywhere from 92 to 98% of that wire that is going through your wire feeder is being deposited into your base metals. Very clean processes. You get high deposition rates, so that means we can put a lot of weld down, big welds in a hurry. Deposition rate, that's how much weld you're actually putting in. Now for GMAW, there's a multiple different types of transfer modes. A transfer mode is how that wire is being melted and it's being fused into your base metal. For this class here, we're typically going to be what they call GMAW short arc, GMAW axle spray. Some just call it spray. The book uses axle spray, so you're using short arc, spray, and we're going to get into some pulse spray applications in this class also. Now I'm going to kind of break this down. I'm going to go over short arc first, go over the process of it. I'll explain to you what it actually is, and I'll go through an actual weld station setup for that process. So that's what we're going to start out with first. GMAW, gas metal arc. When you see that slash S, that S right here is telling me that is short arc, the short arc process. First of all, what is short arc? Here's my welding nozzle, here's my wire that comes through, here's my base metal. So when that wire actually hits, it creates what they call a short arc. Here's my wire coming through my contact tip. You can actually see that the wire, after it makes there, that creates what they call a pinch force on the wire. Like I said, it's creating a short arc. Once that pinch force is created, it actually melts onto the base metal. So the wire comes down, makes contact with the metal, creates a short arc. That short arc heats up the metal, heats up your filler metal. It fuses into your base metal. That happens once this pinch force creates that gap between the wire actually has to come down again, make contact, so this happens very fast. It's constantly being creating that short arc. So every time that wire comes out, makes contact with your base metal, it actually creates that short arc, melting your base metal and your filler metal. Short arc is typically done in thin materials, typically 1/4 inch materials and below. So a lot of your 1/8 inch, 1/16 inch, 3/16. Now you can weld above 1/4 inch, but typically it's done in very thin materials because we're not using quite as much wire feed speed and voltage that we're going to actually be using with some of the other processes. So short arc, thin materials, creates a short arc, metal keeps being fed, creating that short arc constantly, happens very fast. So some of the weld station setups that we're going to be using are going to be basically O35 is what we're going to be using here at the college. O35, when I say O35, that is the diameter of the wire. The diameter is O35. Now you can also use O23, you can use smaller wire diameters, you can go up to O45 wire diameters, but typically the most common is O35 wire. We're going to be using 75% argon and typically a 25% CO2. There's a section just on your shielding gases. I'll go through later on and explain why we're using 75-25 for a gas metal arc welding short circuit. Now, your wire feed speed, let me explain that quickly. Your wire feed speed is how fast your wire is actually coming out of your gun. For example, if I have it set at 200 inches per minute, if I hold that trigger down for 1 minute, 200 inches of wire are going to be fed out of that wire feeder. Typically in our shop, like I said, we're using 75-25, 75% argon, 25% CO2. That is a mixture gas. Typically we're going to run anywhere from about 180 to probably 260 inches per minute. That's our wire feed speed. And we're also going to be using our voltage. This is how much current that we want to be using. So your voltage can range anywhere probably from about 17 to about 22 volts. So this is kind of a setup for your actual welding process. Very, very common process right here. This is probably used in all our industries that run short arc. 1/4 inch below material, old 35 wire, 75% argon, 25% CO2 gas mixture, 180 inches to about 260 inches per minute, anywhere from 17 to 22 volts. So that's short arc. Keep in mind that comes down, makes contact, creates a short arc, pinches that wire off, wire comes back down again. It happens very rapidly. So that's short arc. We'll get more in depth, like I said, about shielding gases and stuff like this. So next, I'm going to go over what they call spray. I know the book goes to globular, but I'm going to jump right to spray transfer mode right now. The main reason being because you can actually see the difference between spray and short arc. When you see GMAW, no letters behind it, that is basically spray transfer. Spray transfer, what actually happens, here's my welding tip, here's the nozzle, here's my wire coming out, here's my base metal. Once that makes contact, it stays at a constant short arc. So your metal actually is being, it's like a spray can. Once your electrode actually hits the base metal, it creates that constant, it's just like a spray can, it sprays fine droplets of filler metal and fuses into your base metal. So as you can tell, typically spray, we weld on 1/4 inch and above materials. Very hard to do a spray transfer on thin metals because your welding currents, your wire feed speed and your voltages are cranked up high, so you usually blow through. For spray to actually occur, we got to be over our transformation temperature. What do I mean transformation temperature? That's where you actually transform that from a liquid into a solid. So you're always welding with that liquid droplets. Where short arc, it comes down, it's a much colder process. So for spray to occur, you got to be above that transformation temperature. Typically that's right around 23 or 24 volts that you have to be welding above. So I'll go through a weld station setup for spray. So when you're in your lab, you can set that up. So actually spray, first of all, we use a lot of the 045 wire diameters. We can use 035. I'll go through 2 different setups. And you can go into 052, 1/16. Typically it's done on bigger wire diameters. So for 045 setup, first of all we're going to be using a 90% argon, 10% CO2. So now you can see our shielding gas actually changed to 10% CO2, 90% argon. We have to have a high rate of argon for that actually to occur. I know some books say 80% to 100, but typically most common practices is 90% argon, 10% CO2. So yeah, you got to have a higher percent argon. The argon actually makes it a more fluid puddle while you're above that transformation temperature. Wire feed speed, typically you're anywhere from like 340 up to about 420 for your wire feed speeds, and those are inches per minute. And typically your volts are going to be anywhere from about 25 to about 30. So as you can see, our volts are way higher than what we were welding at short arc. We have to get that transformation temperature. For old 35 wire, I know we usually start you out, we're still going to be using 90% argon, 10% CO2. Our inches per minute now are typically going to be anywhere from 500 to 700 IPM, inches per minute, and our volts are going to stay about the same. As you can see, a huge difference since we're using a smaller diameter wire. We still need that amount of material going in, so our inches per minute is highly increased when we use volt 35. Now, spray. Think of it as you take a can of spray paint, you spray it onto a piece of metal, and all them fine droplets go. That's how spray occurs. Now, globular. Globular is a mix between spray and short arc. It's right in the middle. So you got short arc, globular, spray transfer. Globular is a little different. We don't hardly do any globular because it's really messy. Industry doesn't do a lot of globular. So as the metal comes down, it comes off in big globs. You get a lot of spatter. You don't have those fine droplets like you do for spray, and you don't have that pinch force like you do on short arc. So globular is right between short arc and spray transfer. So some of the other modes that we're going to kind of go through in this class, GMAW pulse. We just use P. P stands for pulse. Typically this is done in a spray transfer mode. It's spray pulse. Pulse actually means that it actually pulsates. The current actually pulsates. Now what this does is it allows us to do spray transfer when it's a little bit colder. So it gives it a short cooling cycle. So for example, a pulse spray, what you're actually doing is for a short period it jumps up, what they call your peak current, and it drops back down to your background current. A little bit more detail too, and it does that very rapidly. So you have a point in time when you're welding where it's really hot, cools back down to your background current, and it cools that weld put a little bit, jumps back up, jumps back down. It pulsates just like your heart, up, down, and it happens very rapidly. Now this is done in a spray mode, so you're going to be using at least 90% argon. And then you actually, when you go in to set your welder up, when you get on the lab, one of the instructors, because now you're going to actually adjust your volts, you're adjusting your trim or your background current when you actually adjust your pulse. So pulse, also what you're actually doing is adjusting your arc length. What does that mean? Your arc length is the distance between here and there, your base metal, and your electrode. So for example, we could have a very big arc length or a very short arc length. So that's how you adjust your temperature, is your arc length. Alright, the book also goes into buried arc, not very common. I'm not going to go into buried arc, you can read up on it in chapter 10. It also goes into a modulated current. Modulated currents get very common right now. Basically, modulated current is a highly tuned short arc process. So now you can go in and adjust every little thing on your short arc. You can modify it. It's a modulated current. I'm not going to get into that too much because we're not going to be doing that out in the lab. Typically what you're going to be doing in the lab, you're going to be doing a lot of short arc, you're going to be doing a lot of pulse, and you're going to be doing some spray transfer. Alright, next, in GMAW, we're going to talk about filler metals. What is filler metals? That's the wire that is being fed through your wire feed unit. That's what you're using to fuse two metals together. A lot of them are your electrodes too. One of the most common electrodes that we're going to be using out in our shop is what they call ER70S-6. Now there's a whole chapter just on filler metals. I'm not going to get into it too much because I'm going to save that for chapter 28. So your filler metal, main thing is, right now at this point, you see this S, that stands for solid. That's what we're going to be using for all of our GMAW. This is for carbon steel. We're also going to be using what they call ER 4043. This is for aluminum. And we're going to be using some ER 308, 309, 316. These are all stainless steel filler metals. So let's just kind of take a step back. What actually happens? How does this welding actually occur with these base metals and filler metals, electrodes, your welding machine? So the wire is actually being fed through your little whip on your machine. What actually happens when you hit the trigger, the current energizes your contact tip in your whip. So as the wire goes through your contact tip, the contact tip actually energizes that wire with current. So when your wire hits the base metal, it creates that short arc, and it actually melts the metal and the filler metal all at the same time. Now, there's a lot of different types of filler metals. It goes, like I said, from like 0.23 up to 5/32 diameter types of wires. Typically in this class, though, this is going to be your main filler metal, because we're going to be doing a lot of carbon steel. So keep that in mind. So when you go set up your welder, we'll go through a weld station setup too. I'll have a video for that also. Power supplies. Typically, depending on what you want to weld, what you want to do, your power supply is going to determine what type of process. For example, now if you go down to Walmart or Home Depot and you buy one of these little 110 units, now keep in mind, the current that travels through these little units are very small. You're not going to be able to weld a 1/4 inch or 3/8 thick metal. Out here we use 240 and 480 some power supplies. Most of them are all 480, so we have plenty of current to supply our power source. But what type of current are we using? For gas metal arc welding, we are typically going to use what they call DC electrode positive. What does that mean? So it means direct current, electrode, positive. 99.9% of all your wire feed processes use DC electrode positive. So what is actually happening with the DC electrode positive? Here's my welding unit, here's my positive. Now remember, it's electricity, you got to have a negative and a positive to complete that cycle. So that actually means this would be my ground. So this is my base metal right here. Here's my ground clamp. Here's my little wire feeder. I'm going to try drawing. Here's my nozzle, wire feed unit, wire coming down. So current always travels from negative to positive. So what actually happens, the current is traveling to my ground clamp, from my ground clamp up into my wire. That's how that actually occurs. So it's going from negative to positive. So this is our positive terminal, and it keeps that cycle. It's direct. So direct current electrode positive. So it goes through the ground clamp, it's being forced up into that wire, and so on. We talked a little bit about wire feed speed. Your wire feed speed is basically determined by what type of welding process you're doing. It's always it's the inches per minute. Like I said, if I had it set at 200 inches per minute, I hold that trigger down for 1 minute, 200 inches of wire will actually feed through. Shielding gases, GMAW, depending on what type of process you're going to be doing. What is a shielding gas, number one? Number one thing a shielding gas does is it displaces. So as I'm welding, you can see this cone that forms. what it actually does is it displaces the air that we breathe. Because if the air that we breathe actually makes contact with that molten weld puddle, it creates porosity pockets. So it's being forced out. Now, shielding gases are measured in what they call your flow rate. That's how much gas we're actually using. That's called in a volume. It's measured in cubic feet per hour. So a shielding gas, they're coming down through your nozzle, alongside your nozzle. There's some other things shielding gases do. We'll get into shielding gases a little later. Shielding gases, they help you with starting the arc. They help you maintain your arc. But the main thing a shielding gas does is it shields that weld. So as you're welding right here, it's pushing all these atmospheric gases out of the way. It displaces atmospheric gases. We use a lot of argon. Like I said, short arc, 75% argon, 25% CO2, 90% argon, 10% CO2 for spray. Then we're going to be probably the most common gases that we're going to be using. We're also going to be using pure argon when we get into a lot of our non-ferrous metals. So we mentioned two things about gases right now. We mentioned inert gases and reactive gases. So I'm going to kind of go over inert gases. What is an inert gas? It's a non-reactive gas. That's all it is. So like argon. Argon is a very common. Helium is very common inert gas. So these, as we're welding, they do not react, non-reactive to our base metals. We also have reactive gases, just the opposite. CO2 is probably one of the most common, and they do react. Excuse me. What does that mean? So that means as I'm welding, this reactive gas actually reacts with your base metal in your weld puddle. Reactive gases give you much better fusion than inert gases, but in GMAW, typically we're using a mixture of gases. So we're taking the best out of both worlds. So like if we're using 75% argon, 25% CO2, we're using the inert gas. Like I said, number one, it helps with our electrical characteristics and our conductivity. It helps us maintain our arc. We're also going to be using reactive gas, 25% CO2 for short arc, to get fusion. It increases the fusion. Now, to determine what type of mixture we're going to use, like I said, all depends on what type of process we're welding. So, inert gases do not react. Reactive gases do react with your weld puddle. Good electrical characteristics, good fusion. That's the whole idea about gases. That's why we're using a mixture. Now, if we were welding like aluminum, and we're using GMAW process, basically we're going to be using a straight inert gas. Aluminum you cannot mix a reactive gas with. It actually contaminates that weld puddle. And when you get out there and start welding aluminum, you'll see that. Welding's got to be very, very clean. All the metal's got to be super clean when you weld aluminum. And we're just going to use an inert gas when you're welding straight aluminum. So I'm going to cut it off right here. I'll continue on the second part of chapter 10. Make sure you review these, follow the book, and go on. So, thank you.